Hello friends, today we are going to discuss about a very interesting topic from the point of gate. Also, it is important and it is also interesting. It is known as the joining process. It is known as the welding process. Okay. First of all, what we will do is before proceeding towards welding process, we will discuss about something else. Now, what is that? We will be discussing about the joining process first, right? Now, joining process could be anything, not only welding process. Welding process is just a small part of joining process. When you say joining process, the shirt that you wear and you tuck your buttons, yeah, that is also a joining process. The shirt has stitches, so it brings two pieces of cloth together and you get a shirt. That is also a joining process. The zips of your bag is also a joining process. The rivets that you find in bridges, it is also a joining process. Similarly, when you suppose you have a bottle and you put the cap over it, it is also a joining process, right? So on and so forth. There are many different kinds of joining processes, and they are later on classified as you can see over on your screen. I would like to show you one slide. And on this slide, you can see how the joining process is classified and how and where this welding comes up and what we actually need to study from the gate point of view. Alright, so let us have a look at this slide. You can see the joining process has been classified mainly under the heading of mechanical bonding and atomic bonding. And in mechanical bonding, again, there is a temporary bonding and permanent or semi-permanent bonding. Let us talk about the temporary joining process. Temporary joining process means your laces of your shoes, right? Your buttons, your zips of the bag, the Velcro. You understand Velcro? Velcro is something like there are two strips. Velcro is a pair actually, and on one strip there are plastic, what you call needles kind of thing, and on the other strip it is completely threads actually. So when they come together, they get entangled and they form a joint. You must find its use in your sandals and in your shoes also. Okay, it splits up like this. It makes a sound when you open it. Yeah, I know you have got the point. So these are all temporary joining processes, and when you talk about the permanent or semi-permanent joining process, you can see that there is one rivet. Rivet is permanent or semi-permanent, and under this heading it lies. And stitches, as I told you, staples and shrink fits. Staples means those staplers, right? And shrink fits. Now, what is shrink fit? Shrink fit is a very interesting form of joining process. What happens is that let me give you an example. What happens is if you have ever visited your villages or small towns, you will find bullock carts, right? What is bullock cart made up of? It is made up of wood, right? It's the complete structure is made up of wood. But have you seen the wheels of bullock cart? What it is made up of? Again, the wood itself. But the rim of that wheel, have you ever noticed what it is made up of? Yes, it is made up of steel. Okay, so how this steel rim has been put over this, what do you call that, wheel, wooden wheel, right? How they place it over that, and it has to be secured firmly so that it doesn't come out, right? So what happens is, let's say the diameter of this wheel initially is capital D, okay, or let's say D itself. The diameter of this wheel is D mm, or yeah, mm, and the rim or the strip of the steel which has to has to be placed, the complete diameter of that rim will be D minus delta D. It will be a little smaller than the diameter of the wheel itself. And what they do is they heat it up. So upon heating, it expands and its diameter grows to D plus del D. D plus delta D. and then you put it over that. When it cools down, what happens? It will try to contract and it will try to move to its original diameter, which is d minus delta d, but it will be, obviously it will not be able to gain its complete diameter, the initial diameter, because it has been obstructed by the original diameter of the wheel, and this is known as shrink fit. Okay, so it has the wheel has got a rim because of the shrink fit, because of the property of the material, right? So that is also a joining process. Let us proceed further. You will find atomic bonding under the heading of joining process. And atomic bonding, now we are actually moving into welding technology. So you can see there are three categories: solid state atomic bonding, liquid state atomic bonding, and solid or liquid state atomic bonding, right? So in solid state, you will find the cold welding, friction welding, diffusion welding, and hot forge welding. Cold welding is again classified under three things: pressure welding, ultrasonic welding, and explosive welding. Similarly, in liquid state welding, which is also known as fusion welding, right? Why it is known as fusion welding? Because two materials fuse together, two parent metals fuse together, and they form a joint. That means they melt and they form a joint upon solidification. And the liquid state or fusion welding is classified under electric welding and chemical welding. Now, electric welding means you will find different sub-classifications: arc welding, induction welding, and resistance welding. And in chemical welding, you will see gas welding and thermite welding, right? Thermite welding, I used to believe that most of the people know, but when I visited the classrooms, I really got to know that people are not really aware of thermite welding, which is a very common form of kind of welding actually, and it is very interesting. So what happens is that it takes place, or let's say you melt the material because of an exothermic reaction, right? Because of an exothermic reaction, and the heat evolved is so high that it can melt the iron itself, right? So this is nothing but the thermite welding. It is basically used for joining the railroads. You will find its extensive use in joining the railroads or tracks. So what happens is that railroads or these project sites are far into the remotest of areas where there is not proper supply of electricity. So there, this kind of thermite welding, this chemical welding, thermite welding is very useful over there. Okay, so basically what we have done is we have classified the joining process, and we have understood what is the welding process actually, from where it comes up, right? Yeah, it is a small part of joining process. Alright friends, now let us proceed further to the next topic, which is the advantages of welding process. You will find one slide on your screen now. You can see there are n number of advantages of welding operation. Let us have a look, very quick look we will have, because most of the things you already know. So the first point: forms a permanent joint integrated to the workpiece. Would you agree with this or not? Yes, of course it forms a permanent joint. Yeah, we have just now seen under the classification permanent or semi-permanent, right, or temporary joints are there. And the second one is joint can be stronger than the parent metal. Would you agree with this statement or not, that the joints can be stronger than the parent metal itself? Yes, of course, my friends, it is very much possible. Why and how? Let me tell you that while welding, it is possible to alloy the weld bead, right? Now, how you are going to do that? Let me give you some time to think about it. Okay, you start thinking now, but after 15-20 minutes, we will reach a stage where we will be discussing about that. Alright, so till then, just keep thinking. And the third one is it results in metallic continuity between the members. Yes, obviously. And also it is the thermal conductivity and the electrical conductivity is also not hampered because of the welding process. And it is an economical method. Would you agree with this or not? Yes, obviously, so we agree, because the kind of strength we obtain using the welding technology, welding process, it is very economical if you compare that with its cost. Okay, it's very economical. Last one, it is not restricted to factory environment. Just now we discussed about the thermite welding. It is not restricted to the factory environment. Now moving to the disadvantages, right? So every coin has two sides. So every process has its advantages, and now let us see the disadvantages. It needs an expertise, so labor cost is high. Okay, so let me tell you that it needs an expertise. If you want to become a welder, it requires a lot of time and effort and lot of experience to be able to weld properly. Let me tell you that just like in our country, there are many contests or award shows like that. People are awarded for their ability to sing, dance, or to showcase their talent. Let me tell you that in America there is one title which is known as the world's best welder. If you can't believe me, you can Google it. You will find that there is a title which is known as the world's best welder, and people from all over the places, they go over there, they take part in that competition, and they have to weld, and they have to showcase their ability to weld properly. So you will find that welding is a very it is a very respectful job. It requires a lot of effort, time, and experience to reach to that expertise level. Okay, so yeah, that was the first point. And moving to the second point, permanent joint creates problems in deassembling. Yes, obviously, if you want to dismantle something, it cannot be done if it is welded. Now, health issues as hazardous fumes and vapors are produced. Yes, obviously, fumes are produced which could be dangerous for the welder. The last one is poor reliability, so it is not preferred for critical applications. You will find that welding is not used for critical applications because the reliability is an issue. So for doing that, instead of welding, we go for riveting, right? Yes. So these were the disadvantages of welding process, and now we will move to another slide that you can see on your screen, which is known as the applications. Okay, let me give you a little idea, like where this welding, how many kinds of welding processes are there. Firstly, you will get to know about that, and which welding technique is used in which kind of industry and why. You will also gain a little idea from that. So you can see TIG welding, which is tungsten inert gas welding. You must be aware of that. It is extensively used for aerospace industry and nuclear reactors. Why it is used in aerospace industry? Let me tell you that TIG welding is very helpful in joining aluminum. Okay, so if you want to weld aluminum workpieces, TIG should be your first option. Okay, and that is why aerospace, aluminum, you can connect the dots, you can understand, you can follow. Yeah, that is why aerospace industry uses it extensively. SAW is used for heavy engineering. SAW actually, it is known as submerged arc welding operation, and it was developed to join the workpieces at a faster rate. Okay, suppose you have a huge task, you have a huge project, and you have limited time, and you want to weld. It is not possible. And also, if the workpieces are thick workpieces, you have got thick sheet metals, and you want to weld them, the best option, the best choice should be the submerged arc welding operation. And that is why you will find its extensive use in shipbuilding, because the ships are made by using thick workpieces, and the project is so huge that you have to use an operation like this, the SAW welding operation. Alright. Now moving towards GMAW, it is known as gas metal arc welding. It is used for pressure vessels. And now the rest one are common ones. SMAW, it is known as shielded metal arc welding. It is used for general purpose and repairs. Shielded metal arc welding means there will be an arc and it will be shielded using the inert gas. Okay, so it is known as shielded metal arc welding. And then resistance welding, although it is not a part of electric welding that we are going to focus upon today, Just for the extra knowledge, let me tell you, resistance welding is used for automobile industry, and also where extra weight incurred or added because of the filler material, filler rod, we have to go for resistance welding. You must have seen that in Discovery channels or in Nat Geo, you will see that mega factories, I guess, I don't know which channel particularly showcases that, but you must have seen mega factories where they show show the production line of Mercedes and Audi and cars like that. So you must have seen that there will be robots, and these robots will be having the two electrodes like this. They have a clamp like this, and so what happens is that the sheet metals are brought like this, and these robots have a movable arm, and this clamp goes over there and it clamps it like this, passes the huge amount of electricity, and you get a joint. Okay. So this kind of welding is the fastest form of welding. You get the joint within fraction of seconds, right? So this is nothing but the resistance welding. You must have seen that, okay? Yeah. And there is another thing, that is thermite welding. I told you already about that. It is used for rail joints. So particularly, my friends, today what we are going to talk about is, we are not going to talk about the welding technology completely altogether, because it is a huge topic. So what I am doing currently is, I am going to focus upon the electric arc welding, that's all. Alright, so we are not going to talk about the gas welding, no chemical welding, no nothing, only the electric arc welding. And why? Because it is very important from the gate point of view. You will find n number of numerical problems have been asked in the previous years from this particular topic. Okay, so this is what my idea is, to give you the insights about the electric arc welding. Okay, so let us proceed further. Alright, my friends, now the next topic we are going to talk about, you can see on your screens that it is principle of electric arc welding. Now in electric arc welding, first of all, what happens? See, let me give you an idea. Suppose this is your workpiece, alright, and you have an electrode like this. This is your electrode, just assume, and this is the workpiece. Now what will happen is, between the electrode and the workpiece, an arc will be established. Now how it will be established, that is a different theory altogether. We are going to talk about that just after a few moments. Okay, so just imagine that there is an arc being established between the electrode and the workpiece, and what happens is that this arc, because of the formation of arc, huge amount of heat is liberated, and what happens is that the workpiece starts melting. Wherever this arc is striking the workpiece, right, that part starts melting. And also, not only the workpiece, electrode also starts melting. Okay, so the same thing I'm going to show over here, that there is an electrode like this, and it has been connected to a DC power source. For now I am using the DC power source, although AC could also be used. And let's say this L is the length of the arc. Okay, L is the length of the arc, and this is your workpiece, and let's say like this. There is a setup, something like that. So what happens is, now my question to you first of all is that what happens when the arc is established, first of all, and what is happening, that arc is actually, because of the establishment of arc, it is liberating such huge amount of heat energy that workpiece is melting because of that. Why is it happening? What is the logic behind that? Okay, so for that, let me give you a small analogy. Right? You must have seen that the lightning happens during the when the rain happens. So in the clouds, you know already that why the lightning occurs. It happens because of the charges of the clouds. When the two clouds collide together, because of their different charges, the lightning happens. The lightning occurs. But you must have also seen that, or maybe you must have heard perhaps, that these lightning sometimes falls to the ground. and wherever it falls on the ground, suppose it falls in a forest area, now what will happen? It will lead to a forest fire. Okay, you must have seen, you must have witnessed. So what is happening? Why there is a forest fire? Why the huge amount of heat is liberated that entire forest or entire land gets burned up because of that? That is something to analyze, right? To ponder. Another thing is that why and how this lightning is managed. I mean, that is current itself, right? Current is nothing but the flow of electrons. Now, I am in this studio. I am actually surrounded by the electrical wires, right? But I am not getting the shocks or electricity, right? But what happens in case of lightning? Why the lightning or the charges which are like 500 meters above the ground in the clouds, they fall over the earth? How they are able to travel in that air column? You're getting my point. How these charges manage to come down to the earth from the clouds to the land? Yes, because that, if you say, sir, air is a conductor, it doesn't conduct. It is an insulator. It doesn't conduct electricity, right? Then how the charges are flowing down from the clouds to the earth? First question. Because the same thing is happening over here. You will see that this is the electrode and this is the workpiece, and initially there is no arc, but when you switch on the circuit, a arc builds up and starts. You start your welding process. Let me tell you, it is simple to understand. See, what happens is that in case of lightning, there is a huge potential difference. Okay, there is a huge potential difference. Now, what is a potential difference? You will find that there is a huge amount of charges contained in a cloud, and so they want to flow. I mean, if you compare the clouds and the earth, there will be huge potential difference in the amount of charges. So what will happen? This charge will travel from the higher potential to the lower potential, right? And that is why, and because of huge potential difference, what happens? That the air column gets ionized. This air column between the cloud and the earth gets ionized. Now, what is ionization mean? Ionization means that in between there are molecules, these molecules and atoms, and so electrons. So what happens is that ionization means the electrons come out of their orbit, and so suppose there is an atom and it has electrons in it, and what will happen? These electrons will be ejected out, and you have got an ion and a free electron. Now, this free electron is actually responsible for conducting the electricity and also the heat. So you have got an ion and you have got a free electron, something like that. So this is nothing but the ionization process. And now to eject this electron out of its orbit requires a huge amount of energy, right? Now, if the potential difference is too high, these ionization will happen, and few free electrons will be available in that air column, in that particular air column. And when the sufficient amount of free electrons are present, these charges now can travel from the clouds to the earth. Getting the point? The same thing is happening over here. You will find that we will be talking about the arc initiation technique. There are two forms of arc initiation technique. One is touch field, and the other one is first one is touch start. The second one is the field start. Okay, touch start and field start. Touch start and field start. Okay. Now, what is touch start? Touch start, you must have witnessed in your colleges that if you have performed the welding operation in your first year, you will see that what you did was that there was an electrode and you touched first the workpiece, and when you touched, you started passing the electric current, and then you lifted it upwards. You lifted your electrode upwards, and because of this, moving, you're moving this electrode. What is happening is that earlier that current which was flowing, because when they were in contact, now also that the same amount of current is flowing, maybe a little lesser, but the current is still flowing, okay, but you have got an arc now, okay. You will see that even though you have lifted it upwards, there is a constant connect between the workpiece and the electrode in the form of arc. So you have got this arc, and now you can move it and you will get the welding done. The other technique is your field start. So what you will do is, field start is basically used for automated machines, okay. So what happens there is that there will be an electrode and the workpiece, and they will be kept at a small distance away from each other, and little bit of voltage will be applied, okay. So what will happen is that nothing will happen actually. A little bit of voltage will not ionize the arc gap or the air column between this. Then what you will do, you will increase the potential difference. What happened? Something happened. Nothing happened. Again, nothing happened, right? Because the ionization requires a huge amount of potential difference. So a little bit of potential difference is not going to ionize even this amount of air column between electrode and workpiece. So you will keep on increasing the potential difference, and there will be a threshold value of the potential difference at which the arc will strike. And this is the arc initiation through field start. Okay. Now what will happen is, then now once the arc has been initiated, you have to just regulate the arc. I mean, you have to maintain the arc. Maintaining the arc is other issue altogether again. So arc initiation and now maintaining the arc, and then you have to move it for welding your workpiece, right? Now another question to you is that you can see in your screens that a suitable gap is maintained between the workpiece and the electrode. A high current is passed through the circuit. The electric energy is converted into heat energy, producing a temperature of 3000 to 4000 degrees Celsius. This melts the edges to be welded and molten pool is formed. On solidification, a solid joint is obtained. Now another question. So you have understood that how the arc is formed, first of all, because of the huge potential difference. Second thing, that why it leads to melting of the workpiece. What is happening in the arc? Is arc that hot that it can melt the workpiece, or maybe there is something else going on? So let me tell you that what happens. This arc is nothing but, as I told you, it is a flow of electrons. Arcs, the electrons are flowing. Okay, the electrons are flowing through the arc. Now, when the potential difference is high, what happens? The electrons move at a very high speed and it will collide to the workpiece. So electrons move and it collides to the workpiece. Alright, so this is what potential difference does. It increases the speed of these electrons flowing in the circuit. Okay, and when the current is high, the number of electrons increase. Okay, and when the potential difference increases, the speed of the electrons impinging on the workpiece increases. Now what happens? When the electrons are constantly colliding onto the workpiece, this kinetic energy of the electron gets converted into heat energy because they are impinging. And so what happens? Ultimately the workpiece melts, right? Now, okay, fine, you understood how the workpiece melts. But why the electrode melts? Because the electrons are flowing from negative terminal. You can see the electrons. What is the polarity of this electrode? It is negative and workpiece is positive. So you can see that the electrons would be moving from negative to positive and not from positive to negative. But you have also seen that electrodes also melt, right? They are not constant. But why are they melting? Usually the answers students give is, sir, maybe because of the radiation, because a huge amount of heat is being evolved over here. Because of that itself, maybe, electrodes are also melting. But that actually accounts to a very small amount of melting, right? The major thing, the major cause of the melting of the electrode is something else. Now, what is that? As I told you that when the ionization happens, get the free electrons plus you get the ions. Now these ions will be now positively charged ions, right? Electrodes are negative, electrons are negative, ions are positive. Now these positive ions will be moving from positive to negative electron. So you can find that although the electrons are moving in this direction, but the ions are moving from positive to negative. And again the same thing is happening. Ions are colliding or impinging over the electrode, right? But at a lesser speed. So because their kinetic energy is lesser of these ions, so consequently the heat evolved at the electrode, if the electrode is negative, is also lesser. So you will find that the electrode, at the electrode the heat evolved is just the 30% of the total heat evolved. Okay, 70% of heat is evolved at the workpiece. 70% of the heat is evolved at the workpiece, not at the electrode. On electrode only 30%. Right? So this kind of system, my friends, that what you are seeing over here, where the electrode is negative, workpiece is positive, electrons flow from electrode to the workpiece melts at a higher rate because 70% and 30% difference of heat is there. So this kind of system where all these things happen is known as, what it is known as? It is known as state polarity. Okay, and since we are utilizing the direct current over here, it is known as direct current state polarity, DCSP, direct current state polarity. In a similar manner, it has got one more name, let me tell you. It is known as direct current electrode negative, DCEN. In some books you will find DCEN. So it means the same thing, DCSP only, right? Now in a similar manner, can we change the polarity? Yes, obviously the polarity can be changed. The electrode can be made positive and the workpiece could be made negative. Alright, so you will see this is workpiece, again this is the electrode. Okay, and now the electrode has been made positive, workpiece is negative. Now what will happen? When you will switch on the circuit, again you will get the arc. But this time the electrons would be flowing from where to where? From the workpiece to the electrode. And positive ions, what about them? Yes, you are right. They will be flowing from positive to negative, which is your workpiece. Now what about the heat evolved now? Yes, you guessed it right. 70% amount of heat will be evolved at the electrode and only 30% of heat will be evolved on the workpiece. This kind of system is known as what? It is known as direct current reverse polarity and also direct current electrode positive, DCEP. Okay, so these two names are for this kind of system itself. Okay, right. So my friends, so far what you have understood is that what is arc first of all? Arc is nothing but it is the discharge of electrons. How it is generated and why it is generated, right? What happens when it falls over something? Heat is evolved, and why the heat is evolved? Because of the constant impinging of electrons on that particular material. And also you have understood the concept of direct current straight polarity and direct current reverse polarity. Okay. So along with that there is one more case which is ACHF. It is known as ACHF. Now what is ACHF? ACHF is known as alternating current high frequency. Okay. They have got weird names, but these are the names they have got. So we cannot do anything. Okay. And yes, you guessed it right. What must be the case over here? We don't use direct current here. We use AC. The alternating current is used. And because of which, what happens? 50% amount of heat is generated, because after every cycle the polarity changes, right? So this is 50% amount of heat is generated here, and 50% of heat is generated over here. Fine. So you have understood all these three categories. Now it's time to talk about their attributes or the qualities. Now, what about their qualities? Alright friends, so now we are going to talk about the individual properties of all these kind of arrangements. Okay, so have a look here. Since 70% of heat is evolved, what will happen is that you will get a deeper penetration. Okay, if it is known as, there is a term called depth of penetration, right? It is known as depth of penetration. Depth of penetration. Now, what will be the depth of penetration in this case? Will it be higher or lower than this case? Yes, of course it is going to be higher. Why? Because 70% of heat is evolved, right? So that is why it should be higher for this. Okay. And what about, let's say, what kind of metals could be welded using DCSP? You will find, yes, because a huge amount of heat is evolved, high melting point metals can be easily welded. Okay, so high melting point metals can be employed. Now, what about the welding velocity, welding speed? You know, what I can think is, because 30% of heat is evolved on the electrode, say the electrode is a consumable one, so what will happen? It will actually, the electrode will be consumed very slowly, right? Suppose you have a gap in there is a volume that you need to fill up, right? And this electrode is melting very slowly. Then what will happen? You have to stay there for a longer time, and that is why the welding velocity, the rate at which you can proceed further, is going to decrease, right? So what will happen to the welding velocity? You will get it lesser welding velocity. Lesser welding speed. Okay. In a similar manner, you can see for this one, depth of penetration I am writing as DOP is lesser, and lower melting point metals can be joined. And lesser welding speed. Here you will get higher welding speed because 70% of heat is evolved over here. So electrode will be consuming very quickly. So your higher welding speed. Yes. And what about ACHF now? What about ACHF? ACHF is the mediocre form of both of these things. It is the average of all these things, because of 50% of heat evolved, you get moderate depth of penetration, moderate melting point metals could be welded, and moderate welding speed you are going to obtain. Okay, so that is about ACHF. So we have now completed our three following types of arrangements: DCSP, DCRP, and ACHF. Now let us proceed further. Alright, friends, now you can see another slide on your screen, which is the flux. We are going to talk about the flux before we move further. Now, why do we use the flux? Because flux is something that performs very useful functions. Flux does not only perform one single function. You can see that there are lists of functions listed on your screens. Let us have a look. Flux deoxidizes the melt. Do you think deoxidization of the melt is essential? Yes, obviously, because what happens when the metal is heated to a higher temperature, the reactivity of the metal increases manifold. Okay, and that is why there are chances for the contamination because of the atmosphere, the gases surrounding the weld pool, and that is why the covering or the shielding of weld pool is essential. And that is what flux does. It deoxidizes the melt. It absorbs the gases. Very good. And it provides the slag. Why do you need a slag over here? Because the slag is something that floats over the molten metal pool, right? So it is slag is actually used for capturing the impurities, the lighter impurities. They float over the surface of the molten metal, and also slag forms a covering shield, and it disconnects the atmosphere to the molten metal. Okay, so again the same function in a way, and it stabilizes the arc and controls the arc resistivity. It stabilizes the arc. You have seen the arc actually is not stable, it dances all over the places, right? And but what you can stabilize it. Now how you can stabilize that, there is okay, I will tell you later on. There are certain elements or metals that you add in the flux, because of which the stability of the arc increases. Okay. Next is the permits use of different types of current and polarity. It produces smooth weld contour and it reduces the spatter and fumes. And in the next slide you can see that there are certain properties of the flux material, and the first property is density of the flux powder must be lesser than that of the parent material. Would you agree with this? Yes, of course sir, we agree with this, because the flux is supposed to form the slag. Okay, and that is why the density, it needs to float over the molten metal, right? So density has to be lesser than the parent metal. Melting point must be lesser than the parent metal. Melting point should be lesser than the parent metal. Yes, obviously, otherwise the metal would melt, but the flux would not melt, right? Yeah, it should not happen. And it should not produce harmful gases like sulfur dioxide. It is injurious and it is dangerous for the welder. Let us move to the next slide. The next slide says about the filler rod. Now what is a filler rod and why do we use it? Filler rod is the rod, or it is nothing but it is something that provides extra molten metal. Okay, so why do we use it and when do we use it? Let me tell you that I am indicating the butt joint here, you can see. Okay. Now, let's say you have a butt joint which has been profiled like this, right? And it is known as edge preparation. You prepare the edges. And why do you prepare the edges? Can't we simply perform the welding like this by arranging the sheet metals end to end? Why do we need this? Because edge preparation, my friends, is required when the thicknesses are higher. Higher than what? Higher than 5 mm. Okay. So whenever the thicknesses are high of the sheet metal, whenever T is greater than 5 mm, you need to go for profiling or the edge preparation. And whenever the edge preparation is done, some gap is created. You can see the gaps, right? And actually the gaps are created only to increase the strength. And why the strength and how you can increase the strength? It is assumed that, or it is believed that you are going to fill this gap, and when you do this, the strength of the joint is going to increase multiple times. And that is why for higher thicknesses you go for edge preparation, right? And how you are going to fill this gap over here? Of course, you are right, by using the filler rod, right? Yes. So let us see the functions of the filler rod. It supplies additional molten metal to the weld bead. Very good, we have understood. No filler rod for thicknesses lesser than 5 mm. Just now we discussed only for greater than 5 mm thicknesses we use that. And because of the joint preparation, some gap is present. To fill that up, additional metal is required. You have understood it. Now what are the properties of the filler rod? Let us have a look. The density of filler rod must be equal to the density of parent metal. Yes, you agree? Yes. And the melting point of filler rod must be lesser than the parent metal. It should be little lesser because we don't want the parent metal to melt but filler rod is still there, right? Okay. The third one is liquid molten metal of filler rod should be readily miscible with molten metal of parent metal. Yes, obviously, because it has to form a homogeneous mixture over here, right? And until unless it is not forming it should be miscible. It should mix together with the parent metal and the filler rod, yes. And the viscosity of molten metal of filler rod must be as low as possible. Why it should be as low as possible? Because it has to enter the small gaps present between the sheet metals, right? And if its viscosity is high and if it is thick, there are chances it might not penetrate into smaller gaps. Okay, so we try to minimize the viscosity of the filler rods. Very good. So my friends, we have understood the concept of the flux and the filler rod. Now let us move further to the next topic. Alright my friends, now let us have a look at the arc initiation technique. As I told you, there are two kinds of arc initiation technique, and I promise I will tell you. So here it is. So it is the touch start method, and touch start is basically used for manual arc welding operation. What happens, you already know, we have discussed. It is just the elaborated version of it. So let us read it out. In this method, the electrode is brought in contact with the workpiece and then pulled apart to create a very small gap. Touching of electrode causes short circuiting, resulting in flow of heavy current, which in turn leads to heating, partial melting, and even slight evaporation of metal at the electrode tip. Heating of electrode produces free electrons which help in flow of current when electrode is pulled apart. It has to be maintained and stabilized for welding. This is all about your touch initiation method. We will be now looking at the field start method, right? You can note it down. Alright friends, let us have a look at the second kind of arc initiation technique, which is the field start, as we discussed earlier. And you know already what happens, but let us have a look at the notes also. A high strength electric field is applied between the electrode and workpiece, that we know, so that electrons are released, right? Development of high strength field leads to ejection of electrons from the cathode spot. Now what is a cathode spot? My friends, remember one thing, that cathode is the negative electrode, and so this is the electrode, and this will be your cathode spot. So the cathode spot is nothing but it is a spot at which the arc actually meets the electrode. Okay, so cathode spot, then there will be an arc. Arc is meeting the anode at the anode spot, and then anode. Cathode spot, arc, anode spot, and anode. 5 elements. So now once free electrons are available in the arc gap, a normal potential difference between electrode and workpiece ensures flow of charged particles to maintain a welding arc. This process is used for automated process. So I would like to elaborate over the last line. What it is saying, that once the free electrons are produced, so that is what I was telling you. Actually, you need a huge amount of voltage or the potential difference across electrode and workpiece in order to ionize something, ionize the air column between that. Once the air column has been ionized, now you have already got the free electrons, and now you don't need that high voltage or a potential difference across the terminals, right? So that is why, let me tell you now itself, that the threshold voltage at which the ionization happens, right, it is known as open circuit voltage. Okay, it is known as open circuit voltage. And the welding voltage is a little different. So you are going to witness in the numerical problems that welding voltages are very less as compared to the open circuit voltage. I hope that you have got the point. Let us move further. My friends, let me tell you one more thing, that arc, although is nothing but the discharge of electrons and discharge of the charges, but actually it acts like an impedance. It acts like a normal impedance. That means V equal to I, which is the Ohm's law, is very much valid for the arc also. So let's say if the that means my idea to what I mean to say is that arc also has a certain resistance, right? It has a certain resistance, and that is why the voltage across it and the current flowing through it, and its resistance can be equated using the Ohm's law, just like a normal wire, metallic wire. Okay, so keeping that in mind, I'm going to tell you a very important thing about it. So what happens, suppose this is the electrode, and this is the workpiece, and this is the length of the arc L, and now let's say the resistance is, let's say, R1. This is R1 for this first case, when the length of the air column or the arc is L1. Okay, now if this arc length increases, let's say like this, and the length becomes L2, what is going to happen to the resistance? The resistance is going to increase because the length has also increased, just like the normal wire. Okay, right. So R1 and R2, and what will happen to the voltage across that? You know what can happen. You need to equate the Ohm's law, right? Yeah. So if the resistance increases, the flow of electrons through this arc will decrease. That means the current is going to decrease, and what will happen to the potential difference across it? Obviously, it is going to increase, right? So this is what I meant to tell you. And also, you can also remember one thing, that whenever the length will keep on increasing, the potential difference will keep on increasing, because in order to sustain the arc, huge amount of potential difference would be required. Getting the point? Yes. So I hope that you have understood this important concept, and now you are ready to jump to another topic, which is known as the arc welding power source. We are going to talk about the power sources required for arc welding operation. You must have seen the arc welding operation in your colleges also. We don't simply plug the electrode and the workpiece with the normal sockets, and we have a sophisticated equipment which supplies the designated amount of power, and that is what we are going to learn now. Okay, let us proceed. Alright friends, so we were talking about the arc welding power sources, right? So you must have seen a small box, a small unit that supplies sufficient amount of power required, and that box actually could be anything. It could be a transformer, it could be a rectifier, it could be a generator, right? Or the power source could be anything, right? So there is a welding transformer. You must have seen a welding transformer usually supplies AC, and welding rectifier supplies DC. Welding generator can supply anything as per the requirement, AC or DC, and inverter type welding supplies the direct current also. It is DC, right? So these are the welding power sources. Now, what are the characteristics of the welding power sources? Because whenever you go to the market to buy all these things, there should be something, right, that you are actually looking after. That means, what am I looking for? What kind of characteristics one power source should have, right? And depending upon my requirement, what are those characteristics and do they match? Only then I will buy that. Okay, so the next topic we are going to talk about is the characteristic of the arc welding power source, and from where the most number of numericals are asked. Okay, so we are going to very quickly move into that. Alright friends, let us have a look over here. These are the characteristics of the welding power source. Now, when you are purchasing a power source, you need to compare something with something else, with a benchmark. So these are the things that are going to provide that information. Okay. So first thing, the first characteristic is known as OCV, and as you know what is OCV, it is known as open circuit voltage, right? So this is what we are going to talk about. Static characteristics. Now, what are the static characteristics of the power source? We are going to talk about that in detail. And there is a dynamic characteristic. Okay, we are not going to talk about dynamic characteristics because it is beyond the scope of our syllabus. And but for sure, we are going to talk about the current rating and the duty cycle, right? So apart from the dynamic characteristics, we are going to cover everything listed over here, right? Let us talk about OCV. As I told you, open circuit voltage is that voltage when there is no load. So in the no load condition, the current supplied, or in simple words, let me tell you, it is that voltage at which the arc strikes. Let us say like that. Okay, because every time, suppose in the Flux initiation method, you saw that this was the electrode and the workpiece. This was the workpiece, and you kept it like this, and you kept on increasing the voltage. Suppose 10, 20, 30, 40, but you are not obtaining the arc. So there must be some limit, right? There must be some limit at which the arc is going to strike. It is nothing but the open circuit voltage, okay, or at the no load condition, whatever the voltage is there across the electrode and the workpiece is OCV. So let us write down few lines about OCV. I am going to give you the notes. Friends, let us have a look at the OCV and its description. It says it shows the potential difference between two terminals of power source, and optimum value of OCV ranges between 50 to 100 volts depending upon the type of base metal, composition of the electrode coating, type of the welding current, polarity, and the type of welding process, etc. So OCV actually is that threshold voltage at which the arc strikes. And also this voltage is going to depend upon various factors, as you can see, the base metal and the composition of electrode coating. Now, how this composition of electrode coating can help in varying the OCV, let me tell you. This electrode coating, as you know that the electrodes are there are two kinds of electrodes. One is a consumable and non-consumable one. And in consumable also there are two categories. One is coated and another one is bare electrode. Bare electrode means it is not coated with anything at all, just the filler metal, that's all. And the coated electrode contains this coating is nothing but the flux. So you do not need to supply flux additionally or separately. This coating itself acts as a flux. It performs the same function. And you must have seen in the functionality of the flux that it helps in stabilizing the arc. Now what happens is that there are certain elements such as sodium and potassium. They are low in ionization potential. What is ionization potential? Ionization potential means the energy required to convert an atom into an ion, or let's say, let me rephrase it even in a better way. Ionization potential means how much energy is required to eject out the electron from its outer orbit, right? So the metals that have low ionization potential, they can simply eject out, they can liberate the free electrons just like that, even by supplying a little amount of energy, right? And that means you have got a free electron, and now the free electron can conduct the electricity. It can form a conductive path for the rest of the electrons, right? So in this manner, the open circuit voltage, if you have the presence of low ionization potential elements, the open circuit voltage is going to decrease. I hope that you have got the point, right? So this is nothing but the open circuit voltage, and let me tell you, it is indicated by V0. Okay, yeah. So actually, why I'm telling you all this, because we are moving to the most important part of welding operation, as from the gate point of view. In gate examination, they ask one particular kind of numerical problem a lot, quite often, and that is what I'm trying to do here. Okay, I'm trying to explain you that thing, and now this is the beginning. Okay, so we are going to discuss few more terminologies, and we will be solving those numericals. Let us proceed. Alright friends, so have a look here. We are talking about the second parameter under the heading of arc welding power source, which is the static characteristic of power source. Now, what are the static characteristics? Let us define that first. It exhibits the trend of variation in voltage with current when power source is connected to pure resistive load. Now, what is a pure resistive load? It is nothing but the arc itself, right? So, whenever the power source is connected to the arc, or when the welding operation is being performed, arc has been established, then what is the variation of voltage with respect to the current, and vice versa? See, V is equal to IR, right? Or according to the Ohm's law. So if voltage is going to change, I is also going to change. The current is also going to change, and vice versa. So it actually exhibits the trend in variation of these two things. And the variation could be understood or studied under two headings, which is the constant current and constant voltage. So there are two kinds of power sources, my friends. One is the constant current type power sources and constant voltage type power sources. Now, what is the functionality of constant current and constant voltage? We are going to talk about that. It is very interesting and very easy to understand. Okay, let us proceed to the constant current first, and then we will see constant voltage. Alright friends, let us have a look at the constant current type power sources and what are the characteristics of constant current power sources. Let us see. Firstly, let us understand the description. Here, the change in arc voltage causes a very small variation in the welding current. Therefore, it is used for manual metal arc welding operation. Fine, we understood that this is a power source where, and it is designed like that, okay? Let me tell you, these are the power sources that are designed that way. So, what is the property of such power sources? That even if there is a small change in the voltage across the electrode and the workpiece, the current is not going to change that much. Okay, now you are not following what I am saying. Let me tell you, give you an example. Suppose this is the electrode and this is the workpiece, right? And what happens? One more thing. See, therefore it is used for manual metal arc welding operation, right? Manual arc welding operation. Why manual? Because whenever you perform the welding operation, you are holding the electrode with your hand. Human hand is never constant. It is never going to maintain a constant arc length, right? So sometimes the electrode may move up, down, up and a little bit down sometimes, right? And this variation will keep on happening because this is a human hand. You cannot expect it to be perfectly constant throughout the process. So because of which, what happens? Whenever, as I told you, as we discussed earlier, that whenever when the length increases of the arc, what happens? Length has increased according to the Ohm's law. The resistance increases, and when the resistance increases, what happens? The voltage increases across the electrode and the workpiece, and because voltage is increasing, what will happen to the eye? The current will decrease, right? The current will decrease, and this current will decrease, voltage will increase, and the resistance will increase, right? Getting the point? And when the current has decreased, don't you think that welding operation is getting affected because of this change in the length over and over again? Say something. Yeah, I mean, I is going to change, the current is going to change, it is inevitable, you cannot avoid it. In a similar manner, suppose when it comes closer, the resistance is going to decrease and the voltage is going to decrease, therefore I is going to increase. So there will be a constant change in the current, in the level of current drawn, and because of which the weld quality is going to get affected because of that. So what happened was, you went to the market and you asked for the power source, constant current power source, and he gave you some manual, and you saw a graph like this, which is indicating the trend in variation, just like in the definition we have seen, right? And so you saw that because of the change of this much of voltage, VA and VB, there is maybe equal amount of change or variation in the current, right? So you said that I have a sufficient amount of money, I have a good budget, show me a better one. So he told you, he took you to another power source, and what you saw was, the characteristic of that power source was something like this. It was something like this, okay? So, what does it indicate? Let us see. You will see that the variation in the voltage and the current was even smaller than the previous one. So, you will find that for VA, IA is somewhere over here, and for VB, you can see IB is going to be here, right? So corresponding to this voltage and this voltage, there will be two different set of currents, IA and IB. You can see that there is a very small variation over here as compared to this one. So that means the second power source that you saw in your in that shop was the best one. So you purchase that, and you will find whenever you are performing the operation, welding operation, you will see even though my hand shakes, the length is going to change, the voltage is going to change in turn, but I is not changing much. There is no variation in the current. So I hope that you have understood. Sufficient amount of explanation has been given to you. Now let us move to the next kind of power sources, which is known as constant voltage power source, which is actually used for automated machines. Let us have a look. Alright friends, let us have a look at constant voltage type power sources. Let me tell you that this kind of power source is used for automated machines, and why you are going to know right now. Here the arc voltage remains constant during welding despite of the fluctuation in arc length, but it causes a huge variation in the arc current. What does it mean? It means that suppose there is a automated machine, and machine is there, so there is no need to worry about the change in length, right? But what happens is these electrodes, okay, are actually governed. Suppose you are using a consumable electrodes. Just imagine a MIG process or submerged arc welding process where the electrodes are fed automatically. They are fed using the servo controllers, and by sensing the required amount of feed should be given to the electrode, these servo controllers feed the electrodes. I hope that you know already about the MIG welding operation and the SAW welding operation. How the electrodes are present over there. The electrodes are present in the form of electrode wires, and they are wounded over the spools. Okay, and the servo controllers are small wheels, and they keep on feeding the electrode wire. I hope that you have followed. Very good. So what happens is that because it is a machine, it is not going to the length is not going to change much, right? But what happens is that sometimes machine also does some errors. There are certain errors in the computation also. So what happens if you have automated the machine and you want that the machine to take care of itself on its own, and you do not need to interfere, then you will develop a method of self-correction mechanism kind of thing for the machine. So let's say by error, this servo controller fed the electrode wire too much. Okay, a lot of electrode wire was given, and because of which the length, which was the length of the arc, by the way, was supposed to be like this, it has come down like this. Are you getting the point? Yes. So the arc length has decreased. Now when the arc length will decrease, what will happen to the voltage? The length has decreased, and so the resistance has decreased, and because of which the voltage across the electrode and the workpiece has also decreased, right? Very good. So you can see that let's say VB is that voltage, which is the decreased voltage than required. Then you will see that what happens to the current. This is voltage, by the way, and this is current, by the way. So when the voltage decreases, the resistance decreases, what happens to the current? Current is huge. Okay, the voltage has decreased, but the current is going to increase a lot according to this characteristic of this power source. So the power source has been designed in this way that if the voltage is going to dip down even by a small amount, I is going to change a lot, and because of which what will happen, the current has increased, a huge amount of heat will be generated on either sides, maybe the electrode and the workpiece, depending upon the polarity. Now what will happen to the electrode? Electrode will suffer, or it will undergo a lot of heating because of huge amount of current being passed, and this electrode, which was fed earlier very close to the workpiece, is now going to melt. It will be melting, and it will come back to its original size, and the length of the arc will be retained. Getting the point? In a similar manner, if this arc length increases, if the servo controller did not feed the electrode wire at the sufficient rate, what will happen? This length is going to increase, and because the length has increased, what will happen? The resistance has increased, and if the resistance has increased, the voltage across the electrode and the workpiece has increased, and what will happen to the current? Current has decreased. That means the melting of the electrode is going to decrease, and this is how the self-correction can be managed. Anyways, it is being fed continuously, so it will eventually come to its original arc length. Okay, so this kind of mechanism is known as self-regulating arc mechanism, or it is a part of self-correction mechanism, right? And the constant voltage type machines are therefore used for automated machines, okay, where they can regulate themselves, they can correct themselves.